Hello everyone, this is your instructor Asma Mushtaq, and in today's lecture I will explain about one of the applications of the eigenvalues and eigenvectors, that is basically the diagonalization procedure. And this information is very helpful for determining the higher powers of A. For example, if you are having a matrix A and you are interested in computing its higher power like A square, A cube, and up to so on ak, then the eigenvalues and the eigenvectors are helpful for that. Okay, the eigenvalues and eigenvector information contained within a matrix A can be displayed in a useful factorization of the form of A hat is equal to P inverse A P. This factorization enables us to compute a raised to power k quickly for the larger values of k, and then this factorization can be used to analyze the dynamical systems. All right. Generally speaking, we say the eigenvectors diagonalize the matrix. So for an n by n matrix A, means if you are having a matrix A which is of the order of n by n, then we can say that this matrix is diagonalizable if it is similar to a diagonal matrix. Okay, that is, A is diagonalizable if there exists an invertible matrix P such that P inverse AP is diagonal matrix, and this matrix P is said to diagonalize the given matrix A. So for the better understanding, let's say if you are having a square matrix A, you are supposed to construct a matrix P. This matrix P actually consists of what? Eigenvectors of A and what is the property of the eigenvectors that we will use for constructing the matrix P is that they all must be linearly independent. Okay, if you determine the eigenvectors of a matrix A and these matrix vectors are linearly independent, then you can construct a matrix P. And after determining the matrix P, what you need to do, you will find the P inverse and then you will use this formula, and the resultant matrix A will be called the diagonalized matrix. Okay, so let's do an example. Let's say if you are having a matrix A 1 2 2 and 1, and I am interested in diagonalizing this matrix A, then what's the first step? First I will determine its eigenvalues and eigenvectors, and the procedure is same. You will use the or determine the characteristic polynomial for this, which is found using this formula. All right, so 1 minus lambda 2 2 1 minus lambda, fine. And when you will determine its determinant, you can clearly see 1 minus lambda whole square minus 4 is equal to 0. Okay, and then you can just simplify this expression. You will get what? Taking square root on both sides will simplify this expression. So I will have 1 minus lambda is equal to plus minus 2, and from here let's determine the value of lambda. So I will have 1 minus lambda is equal to 2, and this implies what? 1 minus 2 is equal to lambda, so lambda 1 came out to be minus 1. And if you suppose or take the negative value of 2, 1 minus lambda is equal to minus 2, then you can say that minus lambda is equal to minus 2 minus 1, so you will get lambda is equal to 3. So you got the two eigenvalues. that are minus 1 and plus 3. Okay, since these two eigenvalues are distinct, lambda 1 is equal to minus 1 and lambda 2 is equal to 3. Let's just try to find the corresponding eigenvectors. So for lambda is equal to 1 minus 1, substitute the values in the equation a minus lambda I into x is equal to 0, where capital X is the first eigenvector corresponding to the eigenvalue lambda is equal to minus 1. Fine. So we will have 1 minus minus plus 1, then 2, 2, and here I will again have 1 plus 1. You will get basically homogeneous system, and its solution can be easily found using the Gauss elimination. So we will have 2, 2, 2, 2, and the augmented matrix form is written like that. Now I will perform the operation on R2, and this is very simple. R2 minus R1 will result in the elimination of the second row, and using the back substitution procedure you will get 2x1 plus 2x2 is equal to 0, and on further simplification you will get x1 is equal to negative of x2. Let's assume that x2 is equal to minus 1 just to eliminate this negative sign. You could have also chosen some positive value of x2, but it would have resulted in the negative value of x1, so that's why it's totally up to you how you choose. So x1 will be equal to 1. So the first eigenvector corresponding to lambda 1 is equal to lambda 1 is equal to minus 1 is x1 is equal to plus 1, while x2 is equal to minus 1. This is your first eigenvector. Using the same procedure, you can find the second eigenvector, that is actually x2 is equal to 1 comma 1, and I have used the same procedure. Fine. So we got two eigenvectors corresponding to lambda 1 is equal to minus 1, that is actually equal to what, 1 minus 1, and then for lambda is equal to 3 I got 1 comma 1. Fine. As we know, according to the theorem, the eigenvectors corresponding to the distinct eigenvalues, since lambda 1 and lambda 2 both are different eigenvalues, that's why their corresponding eigenvectors x1 and x2 are linearly independent. You can also check how they are linearly independent by constructing the linear combination equation and then finding their constants. If the solution will be only trivial, then obviously these two eigenvectors will be linearly independent vectors. Fine. The second step is to construct the matrix P, and in matrix P we do write the linearly independent eigenvectors as the column vectors. So here P will be equal to 1 minus 1, then 1 1. Once you have found P, the next step is to find the P inverse, that is actually found by finding the adjoint of P over P determinant. Okay, so P determinant is actually 1 plus 1, which is equal to 2, and adjoint of P is equal to what? You have to swap the diagonal entries, and then you just revert the signs of the non-diagonal entries. Okay, fine. So P inverse is actually equal to what? P inverse is equal to 1 over 2 into 1 1 minus 1 and then 1. The next step is to just perform the multiplication, since we know that A is equal to P inverse AP. Okay, so for eliminating P inverse, what I need to do, I can multiply P on both sides, so I will get AP is equal to, or you can also say that just simplify this using the same formula. Let me just do that. P inverse is actually equal to 1 over 2, 1 1 minus 1 and then 1. P inverse, what is A? A was equal to 1 2 2 1, and then you will write the matrix P, that is actually equal to 1 1 minus 1 and 1. I hope it's clear. After multiplying the matrices, you will get the simplified form as 1 over 2 multiple of this square matrix. Okay, and if you now divide all entries of this matrix with the 2, that was actually from the P inverse, or that was the determinant of P, you can see that the resultant matrix, or the result of P inverse A P, is actually equal to 1 over 2 minus 2 0 0 and 6, or minus 1 0 0 and 3. Fine, which is actually the diagonalized matrix. Why it's the diagonal matrix? Because the non-zero entries are residing only on the main diagonal and the rest of the entries are zero. You can also notice one thing, that is the eigenvalues are residing on the main diagonal. Fine, so in this way we have actually diagonalized the given matrix A. Okay, now let's do an example for better understanding the idea how to compute the higher powers of A.